Hello everyone. In this video we're going to be solving a factorial equation. I think we've done a similar problem before, something that looks like this but not the exact one. N factorial is equal to 6 factorial times 7 factorial. And then we're going to solve for n. N is a positive integer. Now notice that n is greater than 7, right? Because we have 7 factorial multiplied by a larger number greater than 1, and that would definitely make that product greater than 7 factorial, which means n should be greater than 7. Okay, great. Now we also should notice that n cannot be prime, because if it is, it has to be greater than 7. And what are some of the primes that are greater than 7? For example, 11, 13, 17. And notice that n cannot be any one of these, because 6 factorial, neither 6 factorial nor 7 factorial can contain one of these primes. All right. So what does that mean? That means n is a composite number. It's not prime. And it's also greater than 7. So it could be 8, 9, 10, 12, 14, so on and so forth. You get the idea? But there are too many options. Obviously, n cannot be too large. Think about it. Can n be 14? 14 factorial is way too large, right? That's definitely has a lot of factors. So it has to be a little smaller. We can keep trying, but there's a better way to do it, and more systematically, because what if these numbers were really large? Instead of 6 factorial and 7 factorial, if we had 2-digit numbers, and by the way, do you think this is going to work for larger numbers? So can we find two numbers whose factorials we can multiply together to produce the factorial of another integer? Good question, right? Something to think about. Let me know what you think in the comment section down below. So let's go ahead and decompose these numbers. Since the answer is composite, hopefully this makes sense. Okay. Great. So I'm going to do the following. I'm going to go ahead and write 6 factorial as 6 times 5 times 4 times 3 times 2 times 1. By the way, 1 doesn't really matter here because it's not really going to help us. I mean, you can just totally ignore it or write it. It's up to you. But when I do the prime factorization, obviously, I'm going to ignore it because 1 is not prime and it's not composite either. Such an interesting number, right? So we can also write this as follows. We have the 2 from here, 2 to the second, and another 2 from here. So that's going to give us 2 to the fourth, which is kind of 16, right? And that kind of makes sense because 7 factorial is 720, and 720 should be divisible by 16, right? Is that correct? I think so, yeah. Anyways, that's the first prime factor. And then if you look at the 3's, there's a 3 here and a 3 here. So that should give us 2 3's or 3 to the second power. And then if you look at the 5, there's only 1. And that's basically it for 6 factorial. In other words, we found the prime factorization of the number. Let's do the same thing for 7 factorial. Just notice that 7 factorial contains 6 factorial. The only difference is 7. So we can write this as 2 to the fourth, 3 to the second, 5 to the first, and 7 to the first. Make sense? Pretty easy. Now, let me tell you something. If your number is very large, like let's say 75 factorial, you don't want to do this because that would take forever. Trust me. There's a better way to do it. Let me show you real quick. You can do this. Let's say we're trying to do the prime factorization of 75 factorial. In and of itself, it's actually a different video, a whole different concept. But let me quickly tell you, you can look at the number of 2's, the number of 3's, the number of 5's in this number, and that can be done by using the floor function. So you can kind of look at this, and then you can kind of look at the second power of 2, which is 4, and then you can look at the 8, so on and so forth, until you can no longer divide, or the greatest integer function or the floor value is going to give you a 0. But again, this looks like a long method. I don't know which one is shorter, but it's just another way to look at it. Anyways, let's get back to our problem. Here we have these two things, and we're going to multiply them together. So when we multiply 6 factorial and 7 factorial together, we're going to get 2 to the 8th, 3 to the 4th, 5 to the 2nd, and 7 to the 1st. Make sense? We just added the exponents. Fairly easy, right? Now here's what we're going to do. we're going to go ahead and split up this number into consecutive factors, such as 1, 2, 3. But wait a minute, we don't really need to worry about 1 because 1 is always going to be there. It's called an empty product. That kind of also explains why 0 to the power 0 is equal to 1. I know some people still insist on that not being 1, but anyways, that's a different story. Go ahead and check out my video. But this can be basically broken down into 2 times 3 times 4 times 5 times 6 times 7. I'm going to go all the way up to 7. At least I'm going to stop at 7 because I know my number is greater than 7, but at least I guaranteed the 7. Obviously, it's going to be more than that, and we're going to deal with the leftovers. But how do I take these out? When I take these out, let's kind of put these in parentheses. And of course, we're going to have other terms, such as, for example, this is 2 to the second power. This is 2 times 3, and everything else is prime. So we have 1, 2, 3, 4 2's. We're using 4 of the 2's, so we should have a 2 to the 4th left over. And then we're using 2 3's, this one and this one. And that leaves us with 3 to the second power because we had 3 to the 4th, remember? And we had 2 to the 8th. 5 to the second, we have 1 5 inside, so we should have another 5 outside. You know what I mean by outside, right? And that's it. We're done. And of course, 7 is inside, so we're good. Now, look at the inside. We have 2, 3, 4, 5, 6, 7. That's 7 factorial without the 1 even, right? So can I make it bigger? Yes. How? I can maybe include an 8. Yes, we have 8. I'll give you an 8, but now I have 2 left. Make sense? And then I need a 9. Do I have a 9? Yes, you do. You can take it. And now we don't have this. We only have 2 here. We don't have this. And we have a 5. But we have a 2 and a 5, which makes 10. Yes, this is the conclusion because we used every factor. You see, you kind of decompose, do the prime factorization, and then you recompose, but in a certain way so that you can get a factorial. Make sense? The product of consecutive integers. And guess what? This is equal to 10 factorial even without 1 because, again, 1 doesn't matter. It doesn't have to be there. It's there, but you don't see it. So what do I have? I have 6 factorial times 7 factorial equals 10 factorial. Is this always true for numbers like this? I don't know. You try to find another example. And this gives us n factorial equals 10 factorial, which means n equals 10. Great. I know you could probably just guess and check real quick. There's definitely another way to do it, right? Because 6 factorial is what? Well, 6 factorial is 720, and then you can kind of write it as 10 times 9 times 8. When you multiply by 7 factorial, of course it becomes 10 factorial, but how would you know? Maybe you do, maybe you don't. Doesn't matter. And this brings us to the end of this video. Thanks for watching. If you enjoyed it, please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.